This video begins our discussion of signals processing, and here we're going to start this discussion by bringing up something that most of you have probably seen before, but we're going to use it to motivate looking at signals in a different way. And so today's topic is the Fourier series. We'll start by reviewing some basic terminology about sinusoidal signals or just anything that's behaving as a sine wave. Here we have a signal that can be defined as yt is equal to a naught plus a sine omega t. And as a reminder, we have the period is defined as the time between the crests of two waves, or you could use the troughs, doesn't matter. And based on the period, we can define the frequency as 1 over t, or the angular frequency as 2 pi f. We also have what we call the DC offset, or A naught, and that's exactly the same as the mean of our signal y. So you can see that as the red dotted line here, and if you were going to calculate this in reality, you would just take the mean of that line. And then the third thing that we'll talk about is the amplitude, which is the maximum magnitude of the wave after the mean has been subtracted off. So how high or low the wave gets above or below its DC offset or mean. If we want to characterize a fluctuating signal, we've got a few ways to do it. One of those is, as we talked about, just trying to find the DC offset, is just take the mean of the signal. So for a continuous signal, we would call that y bar of t, and that's just basically the same as what you saw back in Calculus 2, where it's the integral over some time interval of your signal divided by just the integral of time. Or if you integrate time, it's just the time change from the beginning to the end of the sample that of which you're calculating the mean. If you want the mean of a discrete signal, you simply have to convert the 1 over t2 minus t1 into something that looks like a length of your sample, which in this case is just your sample size, and you have to convert the integral on the top to a sum that takes care of discrete variables. So you've got 1 over n times the sum of all of the y values that you've sampled or from your discretized version of y. And I'll mention that that integral would look like a sum of yi times delta t, but since the denominator is going to be 1 over delta t times n, those delta t's cancel. Then the other thing we can do is look at the fluctuating character of this signal, which is an important task for us when we're trying to determine what's going on with these fluctuations. And we would start by doing this using what's called the root mean square. And this is named as such because you're taking the square root of the mean of squares. So for a continuous signal, that's going to be the same process as above. You're just going to square the y term, the signal term. So you've got the integral of y squared dt divided by the total time record length t2 minus t1, and you just add that square root in there. And just as a note, we still have that same denominator as we had up in the mean equation. I've just gone ahead and skipped the part where we move from the integral to t2 minus t1. And for the discrete case, you've got a similar situation as before, only again, you have to square the y term and you have to put the whole thing under a square root. If we look at an example signal, here I've got a signal that has a DC offset or a mean value of 30, and if we go ahead and subtract the mean from that, or a naught from that, we would call that y prime. So y prime is just the original signal y minus the mean of y, and the reason we do that is shown here on the right plot. You can basically dramatically improve your resolution here by just taking that DC offset out. So now instead of barely being able to see that this signal is wavy, you can see pretty clearly that it's wavy because it allows you to zoom in a little bit better. The other reason we do this is because when we take the RMS of y prime, it looks like this, where on the previous slide you had just a yi squared inside of that summation. Now you've got a yi minus y bar. And hopefully this looks familiar to you, because if you take this limit as n goes to infinity, suddenly this is your standard deviation of your signal. It's just the standard deviation of y. So it's pretty common to take the RMS of y prime rather than y itself. It's also a lot more meaningful, both in terms of characterizing the overall magnitude of your fluctuations, as well as for connecting this with statistics. Now, I just mentioned that what this is effectively doing is characterizing the overall magnitude of your fluctuations, but that's only part of the story, so we need some additional tools. While it's nice to have this RMS that characterizes just the overall fluctuation magnitude, really that doesn't tell us anything about how the signal is fluctuating, what could be the underlying causes of that, and what does that tell us about what we're trying to study. So in order to dig into that portion of a signal or the analysis of a signal, we have to turn to a toolbox that we call Fourier analysis, whereby we break the signal down into its constituent frequencies so that we can gain some more physical insight. And the first step along our path to exploring this topic is to look at the Fourier series. Now, the Fourier series is basically a frequency representation of a function, and any function can be broken down into a Fourier series, which is a DC offset combined with an infinite series of sine and cosine waves. And the coefficients a and bn are called Fourier coefficients. The task now is, how do we determine what the values of an and bn are? That's not entirely clear just from looking at this definition of a Fourier series, so that's going to be the topic of the remainder of this video. Now, when I first learned how to do a Fourier series, I was given a series of definitions of an and bn and just told, hey, these work. And personally, I like to have some idea of why they work. So in order to provide that, it first makes sense to do a very brief discussion of something called inner products. We'll start by talking about something you've probably all seen before, which is the dot product. So if you've got two vectors of length n, so x, which goes from x1 to xn, y that goes from y1 to yn, then you can take the dot product of these two vectors and you end up with something that just looks like the sum of xi times yi across all of the n different components of these vectors. And the meaning of this is it's the projection of x onto y times the magnitude of y. Ultimately, this is where the equation that you probably first learned about dot products came from, where your answer would have been x times cosine of theta. Here, I've drawn a picture that shows essentially what I mean. So if you did x dotted into y and then divided by the magnitude of y, you would get this little projection of x, or rather the length of x in the y direction. And the true dot product would then have that multiplied by that magnitude of y again, and you would end up with something that's a little bit larger. So we can generalize this. It doesn't just have to apply to vectors. We can make a more general version of this that we call the inner product. And specifically, we can apply this to continuous functions. So we typically use these sort of angled brackets to denote an inner product. And if you've got two functions, u and v, then their inner product, instead of being defined with a sum, because these are continuous functions, gets defined with an integral. So on some interval a to b, the inner product is the integral of the product of those two functions. And the meaning here is much the same. It's the projection of u onto v times some appropriate magnitude. So essentially, we can take a look at this and see that u and v take the place of x and y pretty much exactly. And so what this tells us then is, in a sense, how well u is going to match up with v. And so this becomes immediately a strong candidate for trying to determine what our Fourier coefficients are, because we can take our signal and perform an inner product with sine and cosine and use that to determine how well our signal matches up with sine waves and cosine waves. and then use that to come up with a magnitude of each, which corresponds to the A's and B's that we talked about previously. So, long story short, you should just consider the definitions that we're about to show for the coefficients to be the equivalent of a dot product of your signal onto sine and cosine, and that's going to give you the amplitudes that we use for our Fourier series. And when I first realized this was probably not until grad school, but for me personally, this was sort of a sea change in how I thought about and understood problems like this. That's when it really clicked for me, and so I wanted to share that background with you, because in a typical textbook, it's just going to gloss right over that until you get to a higher level. So, how do we use this? Well, we know that the signal can be represented as this series of sine waves, so let's just straight up or take the inner product of these two and determine how the two project onto each other. So if we take the inner product, we still need to find that appropriate magnitude, but we can do that by solving these integrals. So for example, the inner product of yt with cosine is going to give you this equation here, and we'll note that the term with a0 and bn are both going to be 0 here. So you're left with just one term that has the an in it, and you can solve that. An is just going to be a constant, so you can solve the integral of cosine squared using trig identities, and you can do the same thing by taking the inner product with sine and with 1 to come up with bn and a naught respectively. And what you determine are that the Fourier coefficients are defined by these three equations here at the bottom. Next, we'll talk about some useful properties of the Fourier series. For even functions, where y at time t is equal to y at time minus t, for example, for a cosine, bn is going to be identically 0. For an odd function, where y at minus t is equal to minus y at t, such as a sine wave, then an is going to be identically 0. So you can automatically make your life a little bit easier if you just recognize your function as being even or odd. We can also combine a and b such that the definition only uses cosines, and here an and bn would be combined into a cn, and then you would have to take into account this phase function phi n inside, and the definition of these are given here. And this is an important way to deal with these problems, because we can call the cn coefficients an amplitude spectrum, and we can call the phi n coefficients, or rather phase shifts, as we can call that a phase spectra, or a phase spectrum. And these amplitude and phase spectra are going to be absolutely invaluable to us in terms of determining what frequencies dominate a given signal. And then the phase spectrum is perhaps not as widespread useful, but it's got its own set of useful properties that we'll talk about a little later. Next, I'm going to use a square wave to illustrate this process. So the first thing that we'll notice here is that it's got a period of 2. It repeats every 2. Here, I guess I'll call them seconds, even though it's not really important what units are in this example. And we'll note that y bar, or rather the mean of y, is 0. And you can note that by the fact that if you draw a dotted line at y equals 0, it goes right down the middle of this function. And we'll note that at time equals 0, we've got that y at t is equal to minus y at minus t. So this is an odd function, and by definition, all of the an's are going to be 0, and we're left only with bn's. So that means that all we care about are the bn's, and if we perform that integral, which I'll leave to you guys to do as an exercise, then we find that it's going to be equal to this equation here, which is relatively straightforward. And even better, only the odd values of n matter here, because for even n, this is going to be identically 0, since cosine of some even number times pi is 1, so you've got 2 minus 2 in those brackets. So we only care about the bn's for odd n, and those are all going to be equal to 4 over n pi. Relatively straightforward. Generally speaking, an and bn are actually going to be functions of frequency or angular frequency, whatever you happen to prefer working in. So for the square wave we just found, what we're really looking at is that bn or bn times omega, either one. Omega is going to be a constant here. It's just some sort of baseline frequency, multiples of which are where we're finding our frequency points. That's going to be just equal to 4 over pi n. And what we can do is we can plot this. We can plot b as a function of n or as a function of omega. Now the vertical axis here says an. That's a typo. It should say bn. And one of the things that you'll notice is that for the square wave, which is plotted over here, really it's only the first handful of these what we call modes that are containing much amplitude. And you really start, as you increase n, you start losing amplitude rapidly here until eventually it doesn't necessarily make sense to keep going out to n equals infinity. You can probably get by with going out to n equals 5 and you end up with a pretty decent estimate here. Now with a modern computer, maybe that's not such an important consideration because you can pretty easily calculate hundreds of these modes and store them efficiently in just an array in MATLAB, for example. The nice thing here is that this is a really convenient way for characterizing the frequency content of a signal. You can look at a plot like this and immediately see what the dominant frequencies are and how the signal behaves in frequency space, and that's a useful thing to be able to do when you're dealing with any kind of physical phenomenon that is wave-like in nature. You can usually connect this back to the physics at play. Here I have some examples of not just the square wave, but a sawtooth wave and a triangle wave as well, and each one is plotted for 1, 2, 3, and 4 Fourier modes. And as you can see here, generally speaking, more modes means a better approximation. For the triangle wave, it's actually quite great when you look at it. For the square wave, it's not quite as great. And same thing for the sawtooth. And the major difference here is that the square and sawtooth waves have discontinuities, which can cause all kinds of problems. If we dial up the number of modes even further, here I've got the square wave plotted for 4, 10, and 50 modes. You'll see that, near the center of the squares, you start getting a much better agreement between your modeled version, your Fourier model, and the original signal. But right as you get close to those discontinuities, you still see a fair bit of ringing. As you increase the number of modes further, here I've got it plotted with 450 modes. You still have ringing there, and even a very large number of modes is not going to get rid of all of that ringing. And this is a phenomenon known as Gibbs phenomenon. And basically, as you increase the number of modes toward infinity, you can never get rid of that ringing if you've got a discontinuity. It does approach a steady state amplitude, so you do reach a good enough solution eventually, or rather as good as it's going to get solution, but it's never going to go away entirely. And it's important to introduce this here because later when we talk about trying to implement these things practically, we're going to have to be careful about how we implement our analysis methods, because what's going to end up happening is we're going to artificially introduce discontinuities into our signal, and we're going to end up with this ringing that can throw off our answer. So keep that in mind as we move on through the remainder of this unit.